In this video, I'm going to talk about additionality of a nature-based solution. Let's start with a simple example. Let's say that there is some country which is by the ocean, and there is somebody who lives here by the coast, and there is a forest which is in the central part of the country, and this person claims that they're protecting the forest. And they say in the year 2000, we had this forest, and now we're 2020, and the forest continues to exist. It's still the same. And that's because I protected it, so please pay me for my services. This doesn't seem to make sense necessarily because we don't really know whether the person did protect the forest or because the forest didn't need protection, nothing would have happened to it in the first place. So the basic principle of additionality is you want to pay for services rendered. And in fact, we want to pay only for services rendered. And if somebody did not render a service, they shouldn't be paid. So let's take an example. Let's say that was actually a road that had been built just next to the forested area, and there's a branch going off like that. And we all know that when a road is built through a forest, the areas near it are subject to deforestation. And so if the road had been built in this way, and in fact the forest continued to exist, then one might say that perhaps this person was doing something to protect the forest. The problem is even easier to state if you had the following. Let us say that this is the road, I'm just redrawing it in 2000 and 2020, and that we had a forested area right next to the road over here, and that particular area in 2020 had been deforested. So we see that these two forest patches are close to each other and are in similar proximity to a road, but one of them was retained and the other one actually was deforested. So we would say that this appears to be a case for protection to have been done. To be more precise, what we'd like to do is that whenever we have a piece of land, let's call that a pixel because from space, a tract of land looks like a pixel in an image. We want this pixel to be matched to another pixel, and we want the matching to be done in such a way so that these two areas of land, these two pixels, have a very similar set of characteristics. That may be distance from road, it may be the elevation, it may be the soil type and rainfall, etc. So if we then have these two pixels that are matched in this way, then we would expect the evolution of these pixels to have the same path. What do I mean by that? So let's look at this axis over here where time is on this axis. And on this axis, we have the land use. And let us say the land use has just two types. I call that forested for F and deforested for D. And let us say that in the year 2000, we had both pixels to be, I'll call that 1 and 2. So or we call them be more precise, we'll call this the project pixel, and we'll call this the counterfactual or match pixel. And then we'll call that P for project and C for counterfactual. And let's say that in 2000, both project and the counterfactual were forested. And over time, what happened is that the project pixels continued to be forested, but the counterfactual pixels became deforested at this point in time, and then they had this path over here. So when we have this path between the project and the counterfactual pixels, we can say that this gap in land use is due to certain actions taken by the project owner, and therefore the project owner has provided some protection services, and we would like these to be paid for. So in a nutshell, this is how we are managing additionality. Let me go into a little bit more detail now. The first thing we do is we use Earth observations to determine the land use class of all the pixels in a project. So we have, if let's say this is your project, we divide it up into pixel areas, which are all observed from space. And we say the land use class is, for example, forest. And this one is deforested. And let's say small d is degraded and here's another one that's forested, etc. So we can compute the amount of forest that is present in the project area. The second thing we do is we use a matching algorithm, and the matching algorithm gives us a set of counterfactual pixels, the C that I had over here. So it could be that this particular forested area over here, this is a forested area over here, this gets matched to another forested area somewhere else. The degraded area gets matched to another degraded area, and so on. And of course, we're mostly interested in the forested area matchings over time. And so here's the forested area, and that's matched to another forested area. So we get all these matchings, each pixel to another pixel, where these matchings are coming along the dimensions that I've already identified over here. Once you've done the matching, then we compute the evolution of the project and the matching pixel over evolution of the pixels. And so we can draw over here a slightly different graph. We still show time. On this axis, we show the total amount of above ground biomass, which is AGB. And let us say that the project has got a certain amount of above ground biomass. Hopefully it's growing. And we have the counterfactual, which has some kind of above ground biomass. And this above ground biomass may be shrinking due to deforestation or degradation. Now, what we then say is, let us say that the project start is over here. That's the start of project. And that we are looking at the time in the future past the start of project, then the gap between the above ground biomass for the project versus the gap versus that of the counterfactual is then a clear measure of the additionality. So this gap would be the additionality because the project and the counterfactuals would have similar trajectories. In doing this analysis, we have to be careful of some problems that might happen. For instance, one might have a piece of land which has a forest in it, and once the forest is in it, the landowner destroys all of the forest and then plants in it some oil palm. And this oil palm is now shown as increasing the above ground biomass, but they had a preceding deforestation action. In fact, one might even have somebody who did the deforestation specifically in order to have a degraded land and then went and planted something on it and showed that there was a reforestation happening, or at least a resequestration of carbon happening. So if you were to look at the above ground biomass for such a particular project and look at the time, it had some biomass, it went down to zero, and then it's growing back up again in this way. And we don't want this to happen. We don't want somebody to take down a pristine forest and cut it down and regrow it and then say that they should be paid for it. So to prevent this sort of thing, when we're doing the counterfactual, we want to make sure that the counterfactual is well matched for prior to start of project. In other words, when we have this analysis over here, that I'm showing in the box over here, what we're going to do is to make sure that both the project and the counterfactual have the same trajectory, which is essentially constant, unchanged above biomass for the time prior to the project, so that when we do the additionality computation, we are looking at the matched values. To be more precise, let's say I take this graph over here, and I'm going to show the counterfactual in red. If we want to claim additionality for this change in above ground biomass, then we would need to make sure that the counterfactual also had a forest and a degradation, and that the counterfactual, in fact, had lower regrowth, and because of this, there is some additionality over here. If, in fact, the counterfactual were to retain its forest cover in this way, then we would actually have negative additionality in this way. We would have negative additionality in the sense that the project actually has less than the counterfactual, which is of course not a great thing to have. This, I hope, gives a little bit of understanding in how the counterfactuals work and how additionality is done. To summarize, our approach to additionality has the property that we can use Earth observations both to do matching of our project pixels to counterfactual pixels. And the use of counterfactual analysis in this way then gives us the additionality of the project over the counterfactuals. I'll end by saying that we are not looking at individual pixels, but at ensembles of pixels, hundreds of pixels in the project area matched to hundreds of pixels in the counterfactual area. And by doing that, we are not open to manipulation of individual counterfactual pixels. For example, it might be the case that if this particular forested area is matched to this counterfactual pixel, then an attacker, somebody who wants to game the system, would go and actually deforest this bit, in which case they would actually not only get the lumber from the counterfactual pixel, the timber from there, but also they would be getting additionality. So to prevent that from happening, we match a single pixel to a set of pixels like this. And so in this case, the attacker would need to deforest all of these other pixels, which would be a much more difficult task for them to do. And so by doing this extra work, we're able to prevent attacks on the additionality algorithm. Of course, any algorithm such as this might be open to other attacks. And in our research, we continue to be exploring different attacks and how we could stop them from happening.